Carbonyls can be either an amide, an ester, a ketone, an aldehyde, an anhydride, and an acetyl chloride, depending on the groups around the carbonyl. So let's say we have this carbonyl and we react it with a nucleophile. The question is how reactive the carbonyl is to the nucleophilic attack. The rule says that the more partial positive the carbonyl is, implies the more electrophilic it is. And this is going to make it more reactive to the nucleophile. So if we look at the direction of polarization of the carbonyl in there, the carbon is partial positive, the oxygen is partial negative. So the more the partial positive the carbon is, the higher the possibility of the nucleophile to come, attack the carbon, and form a negative charge on the oxygen. So the degree of the electrophilicity of this carbonyl depends on the groups that are attached to the carbonyl. If we have an electron donating group on the carbonyl, electron donating group normally decreases. This is called resonance donation. So they decrease the partial positive charge on the carbonyl of the carbon. So resonance donation, it decreases the partial positive charge at the carbonyl carbon. Same thing for the esters in this case. So esters also can donate electrons by resonance. Acids as well, they can donate electrons by resonance in there. So that is going to decrease the electrophilicity of these carbonyls in there, making the amide the least electrophilic carbon and the least reactive carbon. Considering the ketone in here, we know that CH3 is a slightly donating group. So CH3 is a slightly donating group by inductive effect. So it donates electrons by inductive effect. So also it's going to decrease the electrophilicity of this carbon. So CH3 is a slightly donating group, and it's going again to decrease the electrophilicity. So all of these carbons are not very partial positive in there. This is going to decrease their reactivity when the nucleophile want to attack, because when the nucleophile want to attack, it wants to attack the most electrophilic carbon in there. It still will attack, but the ability for that nucleophile to attack is way less. For the aldehyde, hydrogen, on the other hand, is a slightly electron withdrawing. So this one is going to be slightly, so hydrogen is a slightly electron withdrawing. This is why the carbonyl of the aldehyde is more partial positive than the carbonyl of the ketone. And this is why we say that aldehydes are more reactive than ketone, meaning that if you have both aldehydes and ketones, they are reacting with a nucleophile. The nucleophile will prefer to come and attack the carbonyl of the aldehyde because it's more partial positive than attacking the carbonyl of the ketone. For anhydrides, the carbonyl of the anhydride, so let's consider this carbonyl over here and this carbonyl over here. Now both of these carbonyls, they are connected to oxygen and the chlorine. The oxygen over here is considered to be an electron withdrawing group. Why it's an electron withdrawing group? It's an electron withdrawing group because it's connected to another carbonyl. So it will donate electrons by resonance, but at the same time, it will withdraw electrons by inductive effect. So this oxygen over here is going to withdraw electrons by inductive effect. Same thing for the chlorine. The chlorine also will withdraw electrons by inductive effect in there. And as they withdraw electrons by inductive effect, they are going to make the carbon of the carbonyl more partial positive. So this one is going to be partial positive and this one is going to be partial positive. The chlorine is more electron withdrawing than the oxygen. So that carbon is going to be way more partial positive than this carbon, so it's going to be more reactive. So this is going to be the increasing trend for reactivity for different types of carbonyls. Acid chlorides, they are way more reactive because their carbonyl is way more partial positive than the anhydride, then aldehydes, then ketones, then esters, then amides. The amides are going to be the least reactive because amides, they do donate electrons by resonance. Same thing for esters and carboxylic acids. Another factor for carbonyl reactivity is conjugation. So conjugation, it increases the carbonyl stability and it decreases the carbonyl reactivity. Let's have an example in there. So let's say, for example, if we have a ketone, and we are comparing it to a conjugated ketone over there. So this is a conjugated ketone, and we are comparing those two to a more conjugated ketone. So over here, this is a more conjugated system. This system has 4 p orbitals. This one has 6 p orbitals in there, and this one has 2 p orbitals. So the more p orbitals in there, the more conjugated the system is. So the system is going to be most stable. Let's say, for example, if I have a nucleophile in there that I want to attack. This is going to be the direction of polarization in there where the oxygen pulls electrons away from the carbon, making the carbon partial positive. So always figure out where your electrophilic site, so that the nucleophile will come and attack that electrophilic site. So if the nucleophile comes and attacks that electrophilic site in there, you're going to form a negative charge on the oxygen. Notice what's going to happen in this case. What's going to happen is that the conjugation is going to be broken. So you're going to have a negative charge in here. You still have 2 double bonds and you have a nucleophile in there. So what you did is you introduced an sp3 hybrid carbon in there and you broke the conjugation. So here the conjugation is broken. So breaking the conjugation is going to make that conjugated system to be the least reactive in this case, because you are decreasing the stability of the structure. You started with a most stable structure, but you ended up with a least stable structure in there after the nucleophile attacks. So even though this structure is most stable, however, it's going to be the least reactive towards the nucleophilic attack. This structure over here is going to be the least stable because there is no conjugation. And since there's no conjugation, it's going to be the most reactive. So if I'm looking at the reactivity trend in form of a nucleophile attacking each one of these carbonyls in there, the nucleophile will prefer to attack the carbonyl of the ketone in this example. It's going to attack it faster than it attacks the carbonyl of the conjugated system. So I am expecting that the ketone is going to be the most reactive and the most conjugated system is going to be the least reactive due to when the nucleophile attacks that carbonyl, it breaks the conjugation and it forms a less stable product. Another factor that affects the carbonyl reactivity to the nucleophile attack is the steric hindrance in there. So the steric hindrance normally decreases the carbonyl reactivity to the nucleophilic attack. For example, if we have an aldehyde, a ketone, and a bulky ketone. So let's put a tertiary butyl over there. So let's have 3 R groups around that. And in each one of those, we have a nucleophile, and the nucleophile want to attack the carbonyl. Each of these carbons is partial positive, and in all, this is going to be partial positive, and partial positive electrophile in this case. In all, the nucleophile is going to come and attack the carbon of the carbonyl. But the question is, how accessible is this carbonyl? Start from the lone pair in there. So how accessible is the carbonyl? You can easily see that this hydrogen here is a small group. And because it's a smaller group, the nucleophile can easily reach this carbonyl over here to open the bond and form a negative charge on the oxygen. On the other hand, if you look at the CH3s around the carbonyl in there, these are bigger groups than the hydrogen. So these are considered to be slightly bigger than hydrogen in there. So these are medium groups. And these groups over there are going to hinder the nucleophile a little bit. So the reaction is going to be a little bit slower. So the nucleophile will take more time in order to reach that carbonyl, open the bond, and form a negative charge on the oxygen. So this one is going to be a bit slower in there. This group over compared to this structure over here where you have a bulky group that is hindering the nucleophile from reaching this carbonyl over there. So the reaction will happen here in the nucleophile, will reach the carbonyl, but it's going to be a much slower reaction in this case. So that is going to be a much slower reaction. So if I look at the reactivity of the carbonyls, I would go ahead and rate them like this, where I need no groups or very small groups around the carbonyl so that the nucleophile will attack easily the carbonyl. Remember that an electron withdrawing group also is an important group in there to make that carbonyl more partial positive so that the nucleophile will attack the carbonyl as well.